Welcome back students and participants. A very good morning, good afternoon, good evening to all of you. And as you see, the course title is Multi-Criteria Decision Making in Application, and my good name is Raghunandan Sengupta from the IME department at IIT Kanpur in India. So, this is the continuation of the introduction class, and this is the second lecture out of the 60 lectures, which is basically a 12-week course, and each week we have 5 lectures, each lecture being for half an hour. What is the coverage in this set of lectures? We will consider third, fourth, fifth and sixth example considering the concept of multi-criteria decision making, which we have mentioned in the first set of slides in lecture 1. So, consider the third example. An international construction company wants to take a decision to undertake laying train tracks, and Mr. Abhimanyu Dasgupta, who is the general manager or Department of Civil Engineering for projects for this company, big multinational company, is in charge for building the train tracks in 3 different remote corners of India, which are the Western Ghats, the Northeast India and Central India. So, he and his team has to analyze each project, because there are 3 projects in these 3 different parts of India, and they have to consider based on numerous features, namely the cost, total cost, because the more the difficult the terrain is, more lengthy the track is, more safety features, obviously it will increase the cost. The environment impact, because all these 3 parts of India which I mentioned have a lot of forests there, and mainly in Western Ghats, Central India and Northeast India, and there obviously would be environmental concerns. What is the time taken to complete the project? Longer the time would escalate the cost, longer the time the benefits to the whole population in those areas would be later on, coming up later on, but obviously the utilization has to be done as fast as possible, because it will basically ease the mode of transportation. What is the ease of utilizing different new technologies, trying to lay the track, safety features, whether you are going to use diesel locomotives, electricity locomotives and so on and so forth. What is the availability of skilled labor, because in the central India or in, say for example, Western Ghats, the availability of skilled laborers, people who will work, will be much easier than Northeast India. So, obviously, that will escalate the cost in the part of India which is Northeast India. What is the social relevance and impact? So, whether it will have an environmental impact, whether it will increase the overall economy of that area, whether other modes of communication which is there should not be adversely affected, but it will give a positive benefit for the society in that part. So, all these have to be considered, and the different type of criteria which I mentioned as I was discussing, some may be quantified, many of them may not be quantified. So, Mr. Dasgupta and his team has to analyze each project based on numerous features which I mentioned accordingly. As the team leader, he is aware that the combined budget, total cost, total numbers of engineering experts, laborers who are there, as also the total time available for all these 3 projects are already pre-decided, because if this is a big public project, railways, building a dam, hospital, roads, they will come as a benefit to society, and that benefit has to come as soon as possible. So, shorter the time, you have to basically expedite the work, do it fast, and obviously it will entail cost also, but delaying it also would have different cost implications also. Hence, the total time availability and also in the initial stages, the total cost for these projects are already decided and fixed. Therefore, the different facets Mr. Dasgupta and his team has to consider for all the projects would have distinct impact or importance for these 3 different projects in 3 different parts of India. Hence, the team has to have weights or importance assigned to the above items under different type of criteria they have for the different projects, such that his team, that is Mr. Dasgupta's team, can make judicious decision about how to finish all the 3 assignments, given that the constraints are actually there, and they would definitely constrain and have limitations on all these 3 projects separately. Let us consider the 4th example, and here we will bring some data into the consideration and try to basically give an implication of that. Consider the company Impala Gizima Group, which is based in South Africa, has a large production unit in the Kwega Industrial Development Zone at Port Elizabeth in South Africa. So, that is a big area of development for industrial projects in South Africa. So, what does that company do? It procures 3 different type of items, which are ethylene, propylene and industrial chemicals at cost price, and the costs are given in South African rand. They are per ton, and the cost for these 3 items, ethylene, propylene and industrial chemicals, are respectively 10,000, 9,500 and 11,000. So, what does that company do? The company procures these 3 items to make products, and there are 2 products, which is industrial rubber and industrial plastics, and which is sold in the market to the different type of other industrial companies throughout the world at respective price. Again, the prices are given in South African rand, which is 23,000 per ton and 17,000 per ton. But obviously, there are some limitations and practical limitations, which I will read accordingly. To produce 1 ton of industrial rubber, which is the first product which is produced by this company, they would need 1.25 ton of the first raw material, which is ethylene, 0.5 ton of the second, which is propylene, and 0.25 ton of the third one, which is industrial product. Similarly, if I go to the second output, the requirement of the raw materials respectively would be 0.25 ton, 0.5 and 1.25 ton. Obviously, the second output is industrial plastic, but obviously you cannot, or the company cannot have infinite amount of raw materials and is not able to produce infinite amount of output also, because there is limitation of resources, limitation of manpower, limitations per day, electricity and all these things. So, based on that, the monthly availability of ethylene, propylene and industrial chemical, which are the 3 inputs raw materials, are respectively 200 tons. So, these are given in the monthly basis. It can be on the daily basis, yearly basis, quarterly basis, but we are trying to consider the problem on a unit time scale, which is in per month. So, requirement, let me read it, for the 3 raw materials are respectively 200 tons, 250 tons and 300 tons. While the production constraints, because as I said there would be production constraints, because you cannot produce infinite quantity, per month are maximum of 175 tons for each of these 2 outputs, which is industrial rubber and industrial plastic. So, it can be different also for product 1, product 2, but here we are considering same. Due to market demands, the maximum combined production. So, obviously, the company uses these 3 raw materials, produces the 2 outputs, but they do not have separate production units. So, the combined production per month for these 2 outputs, which as I mentioned is as the industrial chemicals and industrial plastics, total combined is 300 tons per month. Now, with this concept of the input requirement of 3 raw materials, what is the quantum of raw materials utilized to produce these 2 outputs, what is the constraint of the requirement of the raw materials, what is the constraints for the output for the products, what is the combined constraint for the output per products. Based on that, we first formulate the problem as a simple objective function, which may be needed to be maximized or minimized. We will see that in the problem, and what are the constraints. So, if I consider only the revenue function, the revenue, which is the overall input which is coming to the company, is given, I will use this, is given by 23,000 for x 1 and 17,000 for x 2. Now, the question would immediately come up, what do I mean by x 1 and x 2? I did not mention that, there is a reason for that. Now, for any problem when you solve, there are certain sets of decision variables which you need to optimize, and here the decision variables are these two, which is the industrial rubber, which we denote by x 1, which is marked here, and the second one is the industrial plastic, which is denoted by x 2, which is marked here. Now, why are we trying to take only two decision variables? Because depending on the output which you want to maximize the revenues, we will consider the decision variables accordingly. So, the decision variables are two, x 1 and x 2, which I have denoted by the vector x 1 and x 2, and we want to optimize that. Now, based on the revenues, there is a cost function also. So, we will first define the revenue function, the cost function, and later consider a combination of that, we will come to that later. Now, the cost function, if you consider that you are utilizing the inputs, three inputs for both for product 1 and product 2, product 1 being industrial rubber, which is denoted by variable x 1, product 2 in industrial plastic, which is denoted by variable x 2. For the first product, which is x 1, we require 1.25 for the first input, which is the raw material, 0.5, I am not mentioning the units, they are in tons, 0.5 for the second input and 0.25 for the third input. Similarly, for the x 2, which is the industrial plastic, the requirement for the raw materials are respectively for raw material 1, 2 and 3 are given by 0.25, 0.5 and 1.25. So, if I find out, and these factors which I am mentioning, this 10,000, 9,500, 11,000 for the first one, first product of output, then 10,000, 9,500 and again 11,000 are based on the requirement which is there of the inputs. Now, this is the cost function. So, I will denote the revenue function as 1, cost function as 2. Now, if I consider the, obviously, if I consider these two objectives, revenues I want to increase to the maximum, cost I want to decrease to the minimum. But obviously, company, this company which is in South Africa has to basically find out what is the overall net profit. So, profit I am considering, if it is positive, if it is a loss, it will be net loss. So, if I consider the net profit based on the revenues total, cost total, I basically find out the difference between the total revenues and total cost. If I put it using 1 and 2 which is given, I find out the net revenues which I denote by 3 as given, which is 3,000 x 1 minus 4,000 x 2, which is basically x 1 and x 2, you remember, are the decision variables which you want to optimize. Now, if I bring the constraint, so based on the constraints or requirements which I want to produce, the availability of raw materials, the total output which I can do maximum, what is the total combine of the outputs I can do maximum. If I consider this, then for all the constraints which is given, they can be analyzed as this. So, the first one is based on the requirement of constraint 1, which is for the first input, which is the raw material. So, I will denote them as, say for example, A, not 1, 2, 3, 1, 2, 3 was basically for the objectives. B is basically for the constraint based on the second set, C is basically based on the third set. Third set means raw materials 1, 2, 3. Now, if I come to the total allowable output for each of the products, I cannot produce more than 175 for both of them individually. It can change also, but for the problem we have taken it simple. We will denote the fourth constraint as D, fifth constraint as E, and the sixth one, which is the total combined output for decision 1 and decision 2, we will denote it by F. So, for the objective function either denoted by 1 or 2 or 3, the sets of constraints which you can see are given. I have denoted them as A, B, C, D, E, F. Now, bringing that in the picture, I have the problems stated very clearly. First, consider the maximization of the revenue, and if you see I have highlighted the word revenue in bold blue colors, because that will make sense as we proceed with the problem, and why it will make sense you will see that very soon. So, if you want to maximize 1, which is for the revenues. So, this is the revenue function which is given, and obviously revenue as I said I want to increase, and this set of constraint which you see which I am marking are basically slates A, B, C, D, E, F. So, 1, 2, 3, 4, 5, 6 as it is mentioned. So, the first 3 are based on the raw materials, and this 300, 175, 175 which you see on the right hand side are based on the total combined individual amount of output for product 1 and product 2. Now, if we solve this problem and try to maximize the revenue, the overall value which comes out is 135.7 for X 1, which is the first product. These are in tons, and for the second product again in tons is 112.5. Remember, the units are in tons and the time frame is months. So, that part of units and time frame I have made it very simple in order us to understand the problem in the simple way. Now, given this output which is optimal best one, and I will come to that how the overall picture looks like. Why we are able to visualize that in a picture, because that is a 2-dimensional problem, because there are only 2 outputs x 1 and x 2. Obviously, in the 3-dimensional case it will be a 3D figure, which we will consider for other problems later on, and for other 4 or more we have to just solve the problem. Visualizing it and drawing it may not be easy for us. So, considering x 1 and x 2, which is the optimum output for the product 1 and product 2, if I put in the revenue function which was here, which I am circling now, if I put that in the function, the total revenue comes out to be 50,75,000 in South African rand. And very interestingly, I want to mention that if I use these x 1 and x 2 and try to double check whether the constraints are being met, if you put in constraint A, B, I am just mentioning them in the sequence of A, B, C, D, E, F. So, A, B, C, then it was basically D, E, F. If you utilize those 2 outputs and then put output means x 1 and x 2 and try to put them in the constraints, all the constraints are satisfied. That means, they are not violated. For example, the first one would be what? I am just giving an example for the first one, first constraint, which will be 5, which is x 1. X 1 is basically, this is the multiplication sign, this is not x, this is a multiplication sign into 137.5 plus 1, again the multiplication sign into 112.5. If I find that value, it should definitely be less than equal to 100, that 800, which is the first one. Similarly, if I put in the second one, again the multiplication sign, this starts in the multiplication sign. This first value for the decision variable is 137.5 plus 2 multiplied by 112.5 is less than equal to 500. Similarly, I can do it for the third one. The fourth one is what? I'll skip the third one for the timing, because considering the first two is there, you can definitely find out for the third one. For the fourth one, which is given as x 1 plus x 2 is less than equal to 300, I will put it here 137.5 plus 112.5 is less than equal to 300. So, if I add up, so let us consider only I am concentrating on the fourth one, which is here I am highlighting. $137.5, 112.5, this becomes 718, 8, 9, 10, 0 0.1, 314, 5, this will be basically 250. So, obviously 250 is less than equal to 300, which means if I consider the last two, where x 1 and x 2 each individually is less than 175, which is met there, because the first decision variable is 137.5, second one is 112.5. So, having solved that, and obviously as I mentioned, these can be solved using very simple linear programming problem, the prerequisites which I mentioned when I was doing the introduction part. If I solve it and draw and visualize the output, which is a 2-dimensional one, which is easy. So, basically I will plot, for convenience all of us know that I can use and plot the first decision variable x 1 along the x axis, the second decision variable x 2 along the y axis, and obviously it can be changed, there is no problem in that, but is there a convenience based on which I am following. If I see the overall feasible space, the overall feasible space will be given, which I am hashing here. So, in the constraints which I draw in the boundary, they would be based on the fact that there are, if I remember, I am just writing A, B, C, D, E, F. So, these 6 constraints are there, and if you see, the constraints would be giving you this feasible region. So, obviously, there are infinite sets of points in the feasible region, but technically if I consider the concept of linear programming idea, we have to only concentrate the solutions at the corner points. We all know in simple linear programming concept. There is a corner point here also, and there is a corner point here also. And the objective function which you see, which is dotted here, this part, which is the revenue function. This is tilted in a way based on what is the parameter based on which x 1 and x 2 are being multiplied. So, based on the parameters, which was basically the revenue function, if I plot it, and then we all know we have to basically keep shifting the objective function. So, this is basically I am drawing a very random objective function, but the line tiltation is based exact on what are the variables which multiplies x 1 and x 2 in the objective function. So, if I keep moving it to the maximum point, so this is the point which I have, based on which I find out the maximum value. So, the maximum value, if you see, as I mentioned, was 50,75,000 South African rand based on the values of x1 and x2 which I mentioned. This is the point which I will have. So, this will give me the best solution, optimum maximum point for the case when you are trying to maximize the revenue. Now, consider the cost function. So, it is a totally different objective function. So, obviously, if the revenues are to be increased, obvious logic will say that we want to decrease the cost function, hence we use the word or concept of minimization. Again, the constraints are same. If you look at it, the constraints are basically what we are denoted by A, B, C, D, E, F. They are the same, they are not changing. So, first three are based on the combinations of raw material 1, 2, 3 to produce the products which we have denoted the decision variables as x1 and x2. And the last three which you see, which I am putting a double tick mark here, are based on the total quantum of output for x1, for x2 and the combination of x1 and x2, where x1 and x2 are the decision variables. So, if I want to find out the cost function, it is given by 20,000 x1 into 21,000 x2 and we solve it, again using the simple concept of linear programming, because there are linear programming ideas only. When we find, obviously the values are x1 is 0, x2 is 0, that means we should not produce, because we are not considering the revenue function at all, it is only cost. And if you put that 0 0 for x1 and x2 in the objective function which is here, the value will come out to be 0 as it should be. Now, let us again draw it. If I draw that feasible space, again the feasible space does not change because the constraints are same. And the cost function is given as the objective in the cost function in the second problem. Again, if I take the cost function, again I am drawing it very arbitrarily, but interestingly, rather than increasing it, the cost has to be decreased. So, we will move on to the bottom left corner, and the point which gives us the minimum cost is this z star, which is the origin, which is 0 0. So, this is basically the cost function, not the revenue function. Based on that, we basically try to find out the minimum point. See here, just a note, this point where we have maximized the objective, which was the revenue, is this point. Again, infinite sets of feasible points, but based on the concept of linear programming, we find out the corner points, and the corner point which gives us the minimum cost is 0. Finally, let us consider the profit function. Profit function, if you remember, is basically the difference between the revenues and the cost. So, profit is basically to be maximized, and very interestingly, note down the profit function has the parameters based on which we multiply x1 and x2 is 3000 minus 4000 for x2. Again, the sets of variables are exactly the same, A, B, C, D, E, F. When we solve it, the actual values based on which we get the best input for the net profit is 160 0, that means 160 for x1 and 0 for x2. Now, intuitively immediately you will ask why it is 0. Check here, if x2 was basically positive, so obviously this value of minus 4000 x2 would basically bring down the net profit. So, obviously it is much more intuitive to imagine that x2 value would be negative, will be 0, such that that value or the component which adds up to the net profit function would be 0. Based on that, when we utilize this 160 0 for x1 and x2 in the objective function, which is here, the overall net profit comes out to be 4,80,000. Again, let us see, the idea of the feasible set does not change because the constraints are same, and if I take the revenue net profit function, and that net profit function again can be plotted considering is a 2-dimensional one, profit has to be increased. So, if I consider the profit function as this, so it has to be go on to the right hand side, increase. So, the overall best profit point comes out to be Z star, which is 4,80,000 as given. So, with this I will end the second set of slides and consider more examples such that we are in much more comfortable position to start off the ideas of MCTM. Thank you very much and have a nice day.